Good morning to all. Today we will discuss about terminologies with respect to the signal flow graph and some examples based on the signal flow graph. Myself, Mrs. Jyoti Shinde, working as assistant professor in ANTC department, Swedish College of Engineering, Pandharpur. In this, I will discuss about introduction to signal flow graph, definition, terminologies, and some examples on a signal flow graph. Then we will discuss the Mason's gain formula. This gain formula is used for finding the transfer function with the help of signal flow graph. We'll discuss some examples on that. Then we will consider block diagram and we will draw the signal flow graph with the help of block diagram, and then we'll discuss some examples based on that. First, we will discuss what we mean by signal flow graph. This is the nothing but alternative method to block diagram representation which is developed by the scientist Samuel Jefferson Mason. So, for finding the transfer function, it is called as the Mason's gain formula. As we have discussed about the block diagram reduction techniques and we are finding the transfer function with the help of the block diagram, this is another alternative method for finding the transfer function with the help of the signal flow graph, which was designed by the Samuel Jefferson Masons. What's the advantage of this? The availability of the signal flow, availability of a flow graph gain formula are also called Mason's gain formula. A signal flow graph consists of a network in which nodes are connected by directed branches. It depicts the flow of signals from one point of a system to another and gives the relationship amongst the signal. As already we discussed about the block diagram is nothing but output of the first block we have given as the input to the second. In the same way, in the signal flow graph, it consists of the number of nodes and it is connected by the directed branches. A signal flow graph provides the relation between system variables without requiring any reduction procedure. As like in a block diagram, we discussed about how we are going to reduce a block diagram with the help of the rules and regulations, but here it is, reduction is not required, only we're supposed to find out the some variables with respect to the signal flow graph, which is not required any reduction procedure. This is the fundamentals related with the signal flow graph. Consider one example which is having the one input A1 and the output is A2, and the signal flow graph for the equation is shown below as it is directed to one input and one output line is there and it's having some transfer function. In the signal flow graph, every variable in a signal flow graph is designed by the node. Whatever the blue dot is shown, that is nothing but a node. Every transmission function in a signal flow graph is designed by a branch. Here it is, as two nodes are shown by the blue color, and that two nodes are joined up with a directed line that is called as a branch. Always we are supposed to remember all the branches are unidirectional. The arrow in which branch denotes the direction of the signal flow. This is the one example signal flow graph model. Here it is as shown in the PPT. It is having the two equations, y1 of s is equal to and the y2 of s is equal to. Then we will consider the model. It shows the two input r1 of s and the r2 of s and the two outputs y1 of s and the y2 of s. We'll consider first equation, y1 of s is equal to g11 of s into r1 of s plus g12 of s into r2 of s. Then we'll check in the diagram. Here it is, y1 of s is having two input lines. One is from the r1, another one is from the r2, but it's having the unidirectional arrow which is having the transfer function g11 of s and g12 of s. So g11 of s it comes from the r1 of s, so the transfer function multiplied by the input node is r1 of s. And for finding the signal flow graph, we're supposed to consider the algebraic sum of that. So another input is from the R2 of s and the gain is G1 of s. So the final equation is y1 of s is equal to G11 of s into R1 of s plus G12 of s into R2 of s. In the same way, we can apply it for the y2 of s. Y2 of s is also having the two input lines. One is from the R1, another one is from the R2, but its transfer function is different. Whichever the line is comes from the R1 of s, it's having the G2 of s as a transfer function, and another flow or the signal comes from the R2 of s, it is having the G22 of s is a transfer function. So the final equation for the y2 of s is y2 of s is equal to G21 of s into R1 of s plus G22 of s into R2 of s. This is another model for the signal flow graph. R1 and R2 are the inputs, X1 and X2 are the outputs. We'll consider the one equation X1 is equal. Then we can write down the equation with the help of that graph also. If we'll consider the A1 and the X1 and the X2, X1 is having the three input line. One is from the, here it is, that is R1. Another one is a self from, it's from the X1 to X1, and one another one is incoming from the X2. So the equation for the X1 is A11 of X1, as A11 is a transfer function starting from the X1, designated at the same and destination is the same. So A11 into X1 plus another incoming line is from the X2 and the transfer function is A12, so A12 into X2, and the third one is from the R1 and the transfer function is 1, so R1 into 1 is equal to R1. So the final equation is X1 is equal to A11 X1 plus A12 X2 plus R1. We can apply it same for the X2 also. X2 is also having the three input signals. One is from the X1, another one is from the X2, and the third one is from the R2. It's having the transfer function is 1. So the equation is X2 is equal to A21 into X1 plus A22 into X2 plus R2. Then we'll consider the signal flow graph models which shows a number of nodes. We'll consider the, here it is, X0 is the input, X4 is the output node. It's having the number of nodes, that is X0, X1, X2, X3, X4, and it's having its transfer function A, B, C, D, E, F, G and H. It's having the some directions. We can say in this every signal is a unidirectional. It's having the some input and the output along with the transfer function. Here it is, we will consider the some equations, simultaneous equations, and we will consider the signal flow graph and how we are going to construct the signal flow graph with the help of the simultaneous equations. We have here shown the three different equations. X2 is equal to, X3 is equal to, and X4 is equal to. X2 is equal to A21 X1 plus A23 X3. X3 is equal to A31 X1 plus A32 X2 plus A33 into X3. Another equation X4 is equal to A42 into X2 plus A43 into X3. If we consider the all three equations, we can see four different variables in that X1, X2, X3 and X4. Therefore, as this equation is having the four variables, we can consider the four different variables in the signal flow graph as shown in the first diagram. Then we can consider arrange all these nodes from left to right and connect them with the associated branches as like we discussed in the last example. We can consider the first equation X2 is equal to A21 into X1 plus A23 into X3. As shown in the diagram, there are the four different nodes X1, X2, X3 and X4. Out of that, if I'll consider the first equation, X2 is equal to A21 X1, means there is a input line from X1 towards the X2 is having transfer function A21 as shown in the diagram. In the same way, here it is another x3 is there incoming line, and here it is transfer function is a2 3 as shown in the diagram. In the same way we can follow the simultaneous equation provided for the x3 and x4 and we can draw the diagram. Next figure shows another way to arrange the graph. We can draw the signal flow graph by any one of the method. Next, we will discuss some terminologies with respect to the signal flow graph. In the earlier examples, we discussed about what to mean by node, what to mean by the branches. All the branches are unidirectional and whatnot. Now, we will discuss about some terminologies with respect to the signal flow graph. Here it is in the diagram, one signal flow graph is shown. Here it is, one input node is there, that is x1, that is also called as a source node. Then here it is x4 is shown, that is output node, it is also called as a sink node. In other way it is called as input node, output node, or source node and sink node. The next terminology is a path is a continuous or unidirectional succession of branches along which no node is passed more than once. That is, we'll discuss all these things, terminologies, and then we'll go one by one. A forward path is a path from the input node to the output node, that is x1 to x2 to x2 to x4. Forward path is nothing but a starting node and the ending point which follows the only unidirection or the same direction. Then another forward path is there, x1, x2 to x4. Then next terminology is the feedback path. Feedback path or the feedback loop. As its name consists of the loop, their source and the destination point should be same. Then here and we can see in other words, feedback loop is a path which originates and terminates on the same node, that is x2 to x3 and back again to the x2. It's a feedback path. As like we discussed about what I mean by path, x1 to x2, x3 to x4 is another one path is there. Another path is there, x1 to x2 to x4. Another path is there, here it is x2 to x3, x3 to x4. All these are the paths. This is the forward path, x1, x2, x3, x4. There is another forward path, x1 to x2 to x4. This is the feedback loop, x2, x3 and back to the x2. Now we'll discuss some extra terminologies with respect to that. A self loop is a feedback loop consisting of a signal branch, that is A33 is a self loop. Self loop means starting and ending point is same node. The gain of a branch as shown in the diagram, A33 is a self loop. Then the gain of a branch is the transmission function of that branch. As like we discussed about here, it is for the self loop A33, it's a transfer function of the gain of that particular branch. Next, a path gain is a product of a branch gain encountered in traversing a path, that is the gain of the forward path. As like in the last PPT we discussed about two different forward path. If we consider the one forward path, that is x1, x2, x3, x4. Here it is, it's having this transfer function, x1 to x2 is a21, x2 to x3 is a32 and x3 to x4 is a a43. So the product of that one is nothing but a path gain. Then loop gain, here it is a loop gain is a product of the branch gains of the loop, that is loop gain of the feedback loop from x2 to x3 and back to x2. So x1 to x2 to x3, that is a gain x32 and x3 to x2, that is a23. So loop gain is a32 into a23. Next terminology is two loops pass or the loop and the path is said to be non-touching if they have no nodes in a common. Here it is. As we discussed about the terminologies with respect to the signal flow graph, here we will discuss or we will identify the some terminologies with respect to the given signal flow graph. Here it is. One signal flow graph is shown along with their nodes and their path gains. Here it is. We are supposed to find out input node, output node, forward path, feedback path, and we will determine the loop gains. Then we will determine the path gain and how many non-touching loops are there. We'll find out one by one. Here it is. For the given signal flow graph, there are the two forward path. First one is G1, G2, G3, G4, G5 and G7. And the second one is G1, G2, G3, G4, G6 and G7. As it is a forward path, direction of the every flow is unidirectional. Then there are the four loops in the diagram. We will see which are that. First loop is G2 into H1. Loop means, as we have shown, starting point and ending point is same. Here it is a starting point is from the first G2 of S and ending point from the H1 of S to the particular point. Next loop G4 of S into H2 of S. Next loop G4 of S, G5 of S into H3 of S. And the next loop is G4 of S, G6 of S into H3 of S. Then we will find out how many non-touching loops are there. Here it is, as there are the four loops, here it is a three different non-touching loops are there, as we have discussed about what do you mean by non-touching loop. Non-touching loop is nothing but it should not have no single common node. So G2 of S into H1 of S and G4 of S and H2 of S, these two are the non-touching loops. So we are supposed to take a product of that loop gains. In the same way, two different non-touching loop gains are there. We will consider the next signal flow graph and we will follow the same procedure. We will find out the input node, output node, forward path, feedback path, self loop, determine the, we will find out the loop gain and the path gains of the forward path. As shown in the diagram, it's having the one input node and one output node. In another word, we can say X1 is a source node, X8 is the sink node. Next, we will find out the forward paths. First forward path is shown in the diagram by a red line. X1, X2, X3, X4, X5, X6, X7 and X8. It contains another forward path which is from X1 to X2 to X7 to X8. So having the third forward path is from X1 to X2, then X4, X5, X6, X7 and X8. We are supposed to find out the all forward path provided in the signal flow graph. This diagram contains three forward paths. Next, we will find out the feedback paths and how many loops are there in the signal flow graph. We'll consider one by one. First loop is X2, X3, X2. Second one is X3, X4 to X3. Third one is X4, X5, X4. Next one is X5, X6, X5. Next is X6, X7, X6. Next one is X7. Next one is X2, X4, X3, again X2. Next X5, X6, X7, X5. Another loop, x2, x7, x5, x4, x1, x2. Another feedback path or loop, x2, x7, x6, x5, x4, x3, x2. As we discussed about a number of loops, as we discussed about the feedback loops, now we will consider the self loop. It contains only one self loop. Starting and ending point is same. Same means same point. That is x7. Then we will consider as there are the number of loops, we'll consider the gain for all the loop. Then we'll consider the path gains for the forward path. As we have discussed in the first point, it contains the 3 forward path, so it is having the 3 path gains. As we discussed about all the terminologies and all the concepts with respect to the signal flow graph, our aim is to find the transfer function for a given signal flow graph that we are going to find out with the help of the one formula that is called as a Mason's rule and also called as a Mason's gain formula. Mason's it's designed its rule in the year of 1953. The block diagram reduction technique requires successive application of fundamental relationships in order to arrive at the system transfer function. On the other hand, Mason's rule for reducing a signal flow graph to a single transfer function requires the application of only one formula. The formula was derived by S.G. Masons when he related the signal flow graph to the simultaneous equations that can be written from the graph. Here we will discuss the Mason's gain rule for the C of S divided by R of S for a given system signal flow graph. These are the some new concepts with respect to the Mason's formula, where n sign designates the number of forward paths, pi indicates the ith forward path again, delta determinant of the system, delta I is the determinant of the ith forward path. Also, delta is called the signal flow graph determinant or the characteristic function, since delta is equal to 0, the system characteristic equation. Delta is nothing but delta is equal to 1 minus sum of the individual loop gains plus sum of the product of the gains of all possible 2 loops that do not touch each other minus sum of the product of the gains of the all possible through 3 loops that do not touch each other plus and so. Next, delta I is equal to value of the delta for the part of the block diagram that does not touch the ith forward path. Delta I is equal to 1 if there are the non-touching loops to the ith path. If we consider the delta and the delta I, we feel it is somewhat difficult, but we'll go for the solving the example. It will be very easy for finding the transfer function for the given signal flow graph. What procedure we are supposed to follow if I want to use the Mason's gain formula for finding the transfer function for signal flow graph? First point is calculate the how many forward paths are there. As already we have discussed how to find out the forward path. Then calculate all loop transfer functions. Then find out the how many 2 non-touching loops are there. Then find out the how many 3 non-touching loops are there, and so on. Then calculate the delta. Then calculate the delta I for the delta non-touching forward path I. In this way, follow the systematic approach for finding all the points. Once we follow all the 7 steps, we will get a correct transfer function for the given signal flow graph. We will solve some examples on that. Here it is. We'll consider the first example. Example is apply Mason's rule and calculate the transfer function of the system. Here it is, signal flow graph is given. We'll follow the steps, we'll find out the forward paths. Two forward paths are there, P1 and P2. We have written transfer function for that as path again also, that's a G1, G2, G4, and that is for the second path G1, G3 and G4. Next, we'll find out the how many feedback loops are there. There are the 3 feedback loops. Then we'll find out the delta is equal to 1 minus sum of all individual loop gains. Then we'll calculate the delta 1 minus sum of the individual loop gains. Then go for the delta 2. And finally, let's know the equation for Mason's gain formula for finding the transfer function. C divided by R is equal to P1 of delta 1 plus P2 of delta 2. P1 is nothing but a forward part, delta 1 is nothing but the determinant, and P2 as a 2 forward paths are there, P1 into delta 1 plus P2 into delta 2 divided by delta. So the transfer function is G1 G4 in bracket G2 plus G3 divided by 1 minus G1 into G4 into H1 plus G1 G2 G4 into H2 plus G1 G3 G4 into H2. We'll solve some extra examples on that. Next, apply the Mason's rule to calculate the transfer function of the system represented by following signal flow graph. Here it is. We'll follow the same systematic approach for finding the transfer function. First, calculate the forward path. There are the 2 forward paths in that. Then we will write down the gain for that. Then calculate the all loop gains. How many loops are there? Then consider the 2 non-touching loops. Then consider the non-touching 3 non-touching loops. No. Then calculate the delta for the step number 2, 3 and 4. These are the forward path 1, forward path 2. Next example, find the transfer function C of S divided by R of S for the signal flow graph in figure below. There is only one forward path in the diagram, that is G1 of S, G2 of S, G3 of S, G4 of S, G5 of S. Then there are the 4 feedback loops as shown in the diagram, L1, L2, L3 and L4. L1 is G2 of S into H1 of S. L2 is G4 of S into H2 of S. L3 is equal to G7 of S into H4 of S. L4 is equal to G2 of S, G3 of S, G4 of S, G5 of S, G6 of S, G7 of S, G8 of S. Then non-touching loops taken 2 at a once. These 2 are the L1 and L2 is non-touching to each other. L1 and L3 is also non-touching to each other. L2 and the L3 is also non-touching to each other. So 3 non-touching loops are there. Then we'll go for the 3. L1, L2, L3 is also not touching to each other. So 3 non-touching loops are there. Then we will write down the delta. Delta is equal to 1 minus. We'll follow the formula for finding the delta. Then delta 1 is whichever the forward path is there, for that L3 is not touching, so delta 1 is 1 minus G7 of S into H4 of S. It's having only one forward path, so only delta 1 is there. Next, apply the Mason's gain formula for finding the transfer function of the system represented by the following signal flow graph. Already we have discussed about this example, but we'll find out the transfer function for that. This is having the 3 forward paths. Then these are the number of loops. Then we will find out the 2 non-touching loop, 3 non-touching loop. Then as like we have discussed about the signal flow graph, how we can find out the transfer function with the help of the signal flow graph. In the same way, if the block diagram is given, how to find out the transfer function with the help of signal flow graph. but as a block diagram is given, we are supposed to convert that block diagram into signal flow graph. Then this block diagram is shown first. We will convert that block diagram into signal flow graph. Here it is. Whichever the points are there, that first we will show all the nodes R of S, E of S, X1 of S, X2 of X, X3 of X, and C of S, where R of S is the source, C of S is the sink, and whichever the middle E of S, X1, X2, X3, all these are the nodes. Then with the help of whichever the signs are provided and whichever the feedback is there, we are supposed to follow that as shown in the diagram. H2 is a feedback with the minus sign, so minus H2 is there, H3 is also minus, then the G3 is there, minus H1 is there, and finally G4 is there. So with the help of block diagram also, we can use a Meson scan formula for finding the transfer function by converting block diagram into signal flow graph. Then we will follow the same procedure for that, for finding the transfer function with the help of a Meson scan formula. Next example, again signal that block diagram is provided for us. We're supposed to convert that block diagram in that block diagram into signal flow graph. As shown in the diagram, R of S is there, E of S is there, X1, X2, Y1, Y2, and the C of S. We're supposed to consider, or we're supposed to first point out the points, in the block diagram for drawing the signal flow graph. Then follow the whichever the lines are given, whichever the connections are there in between of the all the points along with their gain, whether that is a negative or the positive. Shown in the diagram. So this is the final, that is signal flow graph for the given block diagram. It's having the 7 loops, 3 2 non-touching loops, 4 forward paths, so we have, so we will get here transfer function for the given block diagram. Here we will consider another example. From the block diagram, we are supposed to find out the transfer function with the help of signal flow graph technique. Follow the procedure. First to convert that block diagram into the signal flow graph, and then follow that 7 steps systematic approach for finding the signal transfer function. Then here it is. There are the 2 forward paths along with the gains. 3 feedback loops are there along with their gains. 2 non-touching loops. Delta is equal to, and because the loops touch the nodes of P1 is equal to, therefore delta 1 is equal to 1. Since no loops touch to the node P2, so delta 2 is also is equal to delta. So the transfer function T is equal to P1 delta 1 plus P2 into delta 2 divided by delta. We'll get a transfer function. This is another example. Block diagram is provided. Convert the block diagram into signal flow graph and follow the 7-step systematic approach. This is having the 2 forward paths P1 and P2. There are the 5 feedback loops. All the loops touch the 2 forward. Delta 1 is equal to delta 2 is equal to 1. Hence the transfer function is C divided by R is equal to P1 into delta 1 plus P2 into delta 2 divided by delta. Thank you.